Right, so the topic today is something quite exciting. It's the central tool in extreme graph theory, has been for the last 30 years or so. And it's Semereddy's regularity lemma, sometimes called the uniformity lemma, but more often the regularity lemma. The two mean the same thing. And it's quite a fundamental thing. It says that when you have any graph G, any graph at all, you can find in G a little set of vertices, small, that you have to throw away. And once you've done that, you can partition the rest into sets, a bounded number of these sets, where bounded means that the graph can grow, but the number of sets into which you partition the vertex set is at most some constant that depends on the epsilon I'm going to talk about. And these sets are chosen in such a clever way that the edges between any two of them are distributed in a way in which they would likely be distributed if they were chosen at random. So, once more, there is a partition of the entire vertex set and just few, a bounded number of large, equally sized sets. And they're chosen in such a clever way that when you look at any pair of these sets, then, or any pair except a small number of pairs, exceptional pairs, when you look at such a pair of sets, then the edges between these two sets are distributed uniformly, as they would be if you pick those edges from all the possible edges at random with a probability that is dictated by the number of edges between these two sets. So if you know you want, say, half the possible edges, then given that number half, they will be distributed uniformly as you would expected if they were chosen with probability a half. Right. And this uniformity is measured by a parameter called epsilon. Epsilon, as always in mathematics, is a small real number. And you can choose that as small as you like, positive. And the smaller it is, the more uniform will these edges between different classes be. And you can choose the degree of uniformity that you like, and you have to pay for that by having to allow more sets. But once you've settled on some epsilon, your standard of uniformity, the regularity lemma will return an upper bound, big M, on the number of sets for this partition, which it will tell you exists. So you have few partitions of any graph G, no matter how big G is, into at most big M, many sets, where this big M depends on the quality of the uniformity, this epsilon that you chose at the start. Okay, let me make this more formal. And in order to measure this uniformity, we need to talk about the density of a pair of subsets. So if you have two disjoint sets of vertices in some graph, the density of this pair is the number of actual edges between A and B divided by the number of possible edges. Okay, that's the density. That's what you have there. Oops. The density of the pair AB is the number of edges from A to B divided by order A times order B. Okay. And given any positive epsilon, we call such a pair of vertex set in a given graph epsilon regular if for all subsets x of A and y of B that are not too small, you have the same density between the subsets as you do in between A and B in total, right? So all pairs of subsets that are not too small reflect the overall density between A and B. And that is what I call uniform distribution of edges earlier. Okay? When I say not too small, then the meaning of that is that x is not smaller than epsilon times order A, and y is not smaller than epsilon times order B. So you choose this epsilon once at the start of your Tuesday, and then that will be your measure for all sorts of things to come. For example, for this uniformity, we call this pair epsilon regular if for all sets containing at least an epsilon portion of the bigger sets they're chosen from, the distribution, the density of this pair differs from the density of AB, the overall density, by at most epsilon, right? Always the same reference to epsilon for all x in A and y in B, not too small, i.e. at least epsilon times order A, epsilon times order B. The density between these subsets differs from the density of AB by at most epsilon. Okay. So we use epsilon to decide when a subset of a bigger set is small. We use it to compare densities with reference to epsilon itself. And we use it to compare numbers of edges. So a set of edges of G is going to be small if it's no bigger than epsilon times the number of possible edges on G, namely inches 2, where n is the order of G. Right, so this epsilon, taken in the right context, multiplied by number of vertices, number of possible edges, or taken at net face value, is always going to be our measure of uniformity or of smallness. Okay, so that's an epsilon regular pair of sets, and a partition is epsilon regular, and I think I'll copy that to the board so that we have it for later. So partition V0, V1, Vk of the vertex set of our graph, G is epsilon regular for our fixed given epsilon if few things are satisfied. This V0 is our little exceptional set. So that has to be small. What does small mean? Well, as I pointed out, small means at most epsilon of the reference quantity, which is the order of V itself. I usually abbreviate the number of vertices of G to little n, so whenever you see a little n, that's going to be the order of G. Second, these partition sets, the other ones, have the same size. They all have size which we'll call L. And the third condition is that these pairs, except a few, are epsilon regular. All but at most how many? Well, epsilon times the reference quantity. Reference quantity would be k choose 2, right? If we have k sets, and we're talking about pairs of sets, would be k choose 2. Well, by tradition, we use twice k choose 2. Doesn't really matter. It's just a constant, and this epsilon makes every constant small if we choose it a bit smaller. So for all but few of these pairs, Vi, Vj, all except V0 are epsilon regular. Okay. Right, distinct I and J. Okay, V0 is allowed to be empty. The other Vi are not allowed to be empty. Right? Normally, when we speak of partitions, I always mean partitions into non-empty sets. There's an exception here for V0, which you can think of as the bin of a few vertices about which we can't say anything at all, but there's few of them. And that bin is allowed to be empty if everything works out even more nicely than we had hoped. Okay. Questions about the setup? No? Then I'll state the regularity lemma. Okay. So, Semirady's regularity lemma says that for every epsilon, we're allowed to choose an epsilon at the start, and we're allowed to choose a lower bound on the number of partition sets that we get. We call that little m. There exists this upper bound on the number of partition sets called big M, such that for every G, of order at least m, there exists an epsilon regular partition. Do I have to spell it out, or? Yeah, maybe. Okay, so V0, V1, Vk with k between little m and big M. Right, but this is the important thing. There exists a partition into a bounded number of partition sets where this bound depends only on the epsilon that we have chosen, and of course it has to be bigger than the little m that we have chosen. Okay, the little m serves the purpose of ensuring if we choose little m big, we can influence the amount by which the edges between partition sets exceed the number of edges, possible edges on partition sets. So for example, if we have only 2 partition sets, right, then, if there are half n vertices here and half n vertices there, and then there's a quarter n squared edges between them, but there's half n squared, half n squared half edges on each of those, so that's half that number, so they're very close together. And when the number of partition sets is bigger, then this is not so bad. And that's what this little m is for. So, possible number of edges. Which do I want first? Inside classes, well, the classes have size L, so there's L choose 2 possible edges on each of these classes. So that's k times L choose 2, which is roughly half k L squared edges inside classes, right? And between, how many edges do we have between classes? Well, we have k choose 2 pairs. And between each pair, we have L squared possible edges, right? So that is roughly, this is about half k squared. times L squared edges between classes. And you see that these terms are the same, except here we have k, and here we have k squared. Right? So we can use m, the lower bound on k, to drive up k. If we raise m here, we demand a big M, then the k is going to be big, the number of classes is going to be big, and this difference is going to be big. There's going to be many more edges between classes than on classes. And that's what the little m is for. But the main assertion is that we have few classes bounded by, whose number is bounded by big M. Yes, so that was a bit of a mouthful. Questions about the statement of the regularity lemma? Okay, we'll keep it there so you can see it later. Next concept is a regularity graph. So when we have such a partition, and V0 somewhere in the corner, we have certain densities, different densities between different pairs of partition sets, but these edges are always uniformly distributed. The more so, the smaller we chose our epsilon. And now, if we give ourselves a target density D, some real number between 0 and 1, then we can make an auxiliary graph whose vertices or nodes are going to be the partition classes other than the bin, and in which we make two of these nodes, two classes adjacent, if the density of that particular pair is at least D. So these are not going to be adjacent. Maybe these are going to be adjacent. These two. And this maybe is an isolated vertex in this regularity graph. R. Right? R depends on a particular given partition, epsilon regular partition, and on a parameter D that we use as a threshold for when we put an edge between those two, some two classes, and when we do not. That's the regularity graph corresponding to our partition. And now we blow that up again by replacing every node with some constant number of vertices that we can also choose. So if you choose your favorite S, like 100, we replace every node, every vertex of R, with S little vertices, with 100 little vertices. And whenever there was an edge of R, we make these vertex set completely adjacent. So every vertex sends an edge to every vertex there. Right. So this is a bit like the old G, but only a bit. It's like it because every node that represented an entire big partition class of the vertex set of G is now expanded again to a set of vertices, not normally as big as the original partition class, not nearly as big, but some size that we fix. So every node of R becomes a set of S vertices, and whenever we have an edge in R, we have it because there were lots of edges between these partition classes in G, where lots means the density was at least D. Now, we were free to choose our little d, so that may be 1 over a million. So lots of edges between these classes may be that the density is 1 over a million and a bit, right? And it's not big in absolute terms. But now we make the two S sets fully adjacent. So there are lots of edges between them, all possible edges, very much big in absolute terms. Okay, so from G, we have these partition classes. Each class gets contracted into one node of R, and there are edges of R whenever this pair was dense. Dense just means density bigger than our chosen D. And now every node gets replaced with a set of S vertices, and we make these pairs of S sets completely adjacent whenever there was an edge in R between the nodes these two S sets expand. Okay, are the concepts clear? Right. Then I'll show you a little lemma. So this is a very simple version of a lemma known as the Blowup Lemma. The real Blowup Lemma is a lot more powerful than this, but this is, if you like, the baby version of the Blowup Lemma. And I'll refer to it as a Blowup Lemma from now on. Let me start by giving you an informal idea of what it does. Under certain conditions, which we're going to go through in a moment, this Blowup Lemma tells us that we can find any subgraph of RS, even in G. Okay, once more. RS has these sets of S vertices where G had its vertex classes. And the lemma says that whenever we find a graph H in this RS, we can even find a copy of H in G itself, where when a vertex of H lived in a particular S set, this one here, for example, we can map that vertex of H to G to come to lie in this partition set. And another vertex of H that was in this S set in RS can be mapped to this partition class of G in such a way that this edge here, if H uses that edge, is indeed an edge of G. Right? For RS, this is trivial because all these edges exist in RS whenever this was a blue edge, right, an edge of R. But in G, it's going to be more tricky to find a pair of vertices of G in these respective classes to map out to vertices of H2 so that they're really adjacent if they need to be because they're adjacent in H. Right, so the lemma, the Blowup lemma says that graphs H that can be found as subgraphs in RS can also be found in G under certain conditions that we're going to walk through now. So what are the conditions? The conditions is that we can specify little d. D is the density threshold, and it doesn't matter if d is really, really small, right? If d is small, our task of finding H and G will be a lot harder than when d is big, right? Because when d is small, there are few edges between these partition classes. But that's fine. We can specify any d that we like as small as possible. We can also specify a big delta. We'll get to that in a moment. You can think of that as the bound on the maximum degree of H. Right? This lemma works only for graphs H, which have their maximum degree bounded by a big delta that we have to input into this Blowup lemma at the start. So given a little d, a density as small as we like, and this bound big delta on the max degree of H, this lemma returns an epsilon, which it calls epsilon naught, so that whenever we have a regularity graph whose epsilon in the epsilon regular partition of a graph G on which it was built is smaller than this epsilon naught. Whenever we have a regularity graph coming from a small epsilon, smaller than epsilon naught, regular partition of a graph G, and any number s that we dreamt up, little s, then the lemma assures us that any h of max degree at most delta that we can find in Ks can also be found in G. And there is one more condition that we must satisfy, and that is that the classes of our epsilon regular partition have to be big. This L has to be big in terms of little d, big delta, and S. And this is how it depends on them. So we need bigger classes. Little l has to be bigger, right? Bigger, when the classes are bigger, that helps us find H in G, right? And we need these classes to be bigger. When S is bigger, yes, of course. When S is bigger, it makes it easier for us to embed H in RS. So we can embed more H's. And obviously, that comes at a price. And the price is that the classes of G to which these S sets correspond will have to be a lot bigger too. So L has to be bigger when S is big. It also has to be bigger when D is small. Also clear, right? When D is small, then the translation from finding H in RS to finding H in G has to work with epsilon regular pairs of much smaller, of smaller density D. Because when little d is small, then R has lots of edges, right? We're not asking a lot of an epsilon regular pair in order to put a blue edge between the nodes of R. So when D is small, when we allow R to have lots of edges, then that is going to make it more difficult to find H in G, and therefore the partition classes have to be bigger to make up for that, right? And so this L has to be bigger when S is big, it has to be bigger when little d is small, and it also has to be bigger when the max degree, big delta, is big. Right, because that allows for more H to be embedded, right? And it makes it harder for us to embed them. Okay. So if you go through the quantifiers, then let's just do that slowly again. Notice that we can choose D at the start of the day. Right? Little d is our density parameter, and we can choose that as small as we like, as long as it's bigger than 0. Then epsilon will be returned by the lemma, so it will tell us to make epsilon small, depending on the d that we chose. If we make d really small, then epsilon will have to be tiny. The lemma will tell us how small to choose epsilon so that the whole thing works. Then it's our turn, and we can wish for little s. So by the time we wish for s, little s, the epsilon is already fixed. Right? The epsilon depends only on the d, and on the big D, on delta. Right? And then we have our epsilon, and then we can ask for little s vertices to be in our classes here in RS. And the only way in which we have to pay for doing that is by making the classes bigger. Right? D and epsilon are now fixed. If we choose s, little s big, if we want big classes, which makes it easy to embed H in RS, then we have to pay for that by allowing the partition classes of G to be really big as well. All right? And the lemma will tell us how big. Before we prove the Blowup Lemma, we need another little tool, and that's a very natural lemma that looks technical, but is really, really standard and the sort of thing you'd expect. And what does it do? It tells you something about degrees in an epsilon regular pair. So we have an epsilon regular pair of density some d between 0 and 1, and we're asking for a subset y of b, the pair is AB, that is not too small, so not too small is measured in terms of epsilon, as always, has size at least epsilon order b. How many vertices, how many edges a given vertex sends to y? Right? And, well, the entire density of this pair AB is D. Right? So, on average, a vertex sends D times order B edges across. Right? A portion of D of all possible edges exists. So on average, a person is adjacent to the same proportion, D, of its potential neighbors, all the vertices in B. And the lemma says that most vertices here do the same even for this set Y. So the number of edges they send to Y is about D times the size of Y, the same proportion. More precisely, at least D minus epsilon times order Y, right? Same thing, epsilon is our universal sort of error term, right? Epsilon times the relevant number. Here the relevant number is the reference number is the size of B, and the size subset of B is big if it has at least epsilon times that many vertices. Here the reference quantity is D, and we deviate from D by at most epsilon when we count the number of edges that a particular vertex sends to this arbitrary size Y that is not too small. Right? So that is the assertion that this holds for most vertices. What is most vertices? Well, all of them except fewer than epsilon times order A. For all V in A except at most epsilon A many. Right? It looks a bit technical, but it's really, really easy to prove. Because let's just consider the set of those vertices in A, call that set X, that are not as we would like them. So let X be the set of vertices that send fewer than this number of edges to Y. Right? Then you can see that the number of edges from X to Y is, well, for every vertex in X, you have fewer than the required number, fewer than this number edges across. So the entire set of edges between X and Y is how big? Order X times that number, smaller than that. Order X times D minus E times order Y. That's the number of edges. Just under that quantity is the number of edges between X and Y. Order X times this, times D minus epsilon, times order Y. Now divide that number by order X and divide it by order Y, and then you have the density between X and Y is less than D minus epsilon. But it shouldn't be. That contradicts epsilon regularity if this set X is also not too small. Right? If this has size at least epsilon order A. Since we are epsilon regular, we can't have a contradiction to epsilon regularity. So the only solution is that this X is smaller than epsilon times order A. And that's the statement of the lemma. So for the Blowup lemma, at the end of the day, we want to find a subgraph H of RS somewhere in G. So remember that RS has partition classes, all of size S, little s, that's the little s that we could choose in the lemma here. So S vertices in each of these classes in RS. And we assume that we have a graph that we want to embed in G let's see, I wanted the edges. Something like this. So this is our graph H. Let's call these vertices of H U1, U2, U3, and so on. And our aim is to embed them in the same or corresponding partition classes that correspond to their classes where they live in RS. Right, remember that these classes here come from the original partition classes of our epsilon regular partition of G. And so we want to embed U1 somewhere here in this same class that corresponds to this class. I call that V1. U2 should get mapped to the same corresponding class as well. The image will be called V2. And we're going to embed those vertices one by one inductively. And let's have a look at how we can do that in a way that is not too dumb. Suppose we have embedded U1 in the right class called the image V1. Then the neighbors of U1 in H will later also be mapped to their corresponding classes, but the images must be neighbors of V1. So for those neighbors of U1 in H, and in this case, they're U3, U4, and this one, the freedom that we have in embedding those later vertices is restricted. So vertices that are adjacent to U1 there have to be mapped to certain subsets of their target class, which I'm indicating in blue to remind you that we're talking about target sets for embedding neighbors of U1 that should in G be adjacent to V1. So when we then embed U2, and we have found V2 up there already, then the common neighbors, or then the neighbors of U2 must be mapped to neighbors of V2. And if they're also neighbors of U1, then the target set for those neighbors will lie inside the blue sets. So U3 is a common neighbor, and therefore we have to map U3 to a vertex that is adjacent to both V1 and V2, and so that will sit in this smaller target set. U4 is also adjacent to U1 and U2, So U4 also has to be mapped into such a smaller set, but U4 is in fact also adjacent to U3, so the target set gets even smaller. And eventually V4 will sit inside this smaller target set, and so on. The target set for VI will originally just be the entire class, the partition class that corresponds to the partition class of RS in which UI lies. But then it shrinks with every little uj, j less than I, that we embed earlier, and to which UI is adjacent. Right? When we embed an earlier vertex of H, and our UI is adjacent to that earlier vertex, then VI must be adjacent to the image of that uj. So the target set for the target set yi for VI will be restricted to the neighborhood of that Vj. So eventually we'll arrive at the actual vertex Vi that is going to be the image of Ui. And the task is now, when we embed uj, to find an image Vj that is adjacent, that sends many edges to each of the target sets for the neighbors of uj. Right? So this uj has certain neighbors ui, maybe 5. Now we want to embed uj, find a vj, and the idea is to choose vj in such a way that it sends edges, many edges, to all the target sets of the vi for which ui is adjacent to the uj that we're embedding now. We shall be using this little lemma that I showed you earlier to find a vertex that sends many edges to these target sets. Remember the lemma I showed you earlier had this form that we have a certain target set called y on the right, then most vertices on the left send many edges there. A few don't, but those that don't have, there are fewer than epsilon times order A of them, so we throw them away. So we have a target set here, we have the blue target set for V3, and then we had to embed U2, and we embedded U2 in such a way that its image V2 should send lots of edges to this blue set here. And V2 should also send lots of edges to this blue set here. Can we find such a V2? Yes, we can. If the target set from which we have to choose V2, it also has a target set, is big enough such that deleting the useless images doesn't make it too small. Which images are useless? Well, those that don't send enough edges to this blue set, or don't send enough edges to this blue set, and so on. For every blue set, how many vertices are useless? Well, fewer than epsilon times little l, size of that class, many. And this is depicted here. When we restrict the target set, the blue sets, for a later Vi to the neighborhood of Vj that we want to find, we require that this target set shrinks by a factor of no more than d minus epsilon. Ideally d, but we can't always manage that. See the previous little lemma. But we can find many, we can find vertices that send many edges to a portion of the current target set that is obtained from it by a factor of d minus epsilon. So fewer than epsilon times L, little l, vertices from the current target set of Vj are useless. But that doesn't matter because the target set, the current target set for Uj, how was that obtained from the original partition class? Like every target set, it shrank in every step by a factor of at most d minus epsilon. Not by a smaller factor. Right? So how often did it shrink? Well, every time the target set for Uj shrank every time we embedded an earlier neighbor of Uj. How many times is that? Well, at most as many times as Uj has neighbors. How many neighbors does Uj have? Delta, big delta. And that is our bounded quantity. So since H has degree at most delta, and delta is some fixed number now, we know that we had at most delta steps in which the target set for Vj shrank by a factor of d minus epsilon. At most, big delta times. And there's another restriction. We might, from that set, have previously chosen some other V somethings, right? We don't know where we embedded those, so they might accidentally lie in the target set for Vj. How many of those are there? Well, in the same target set, there were at most S vertices embedded, because only vertices from the correct class get embedded in that same class. So we need that the size of the target set of Vj, after deleting little l useless vertices, still exceeds the number of vertices previously embedded in that class, which is fewer than S. And then the Blowup Lemma works if L is big enough in terms of this S and D and delta. And we can simply ensure that it's big enough by making M big. I hope that at least the idea was clear. That we reserve these target sets. They shrink every time we embed one vertex. We embed the vertices cleverly so that they send many edges to the target sets of their later neighbors. And we can find such clever embeddings by the little lemma that we had earlier, which rules out only few candidates for the image of Vj, Uj as useless.